Now let's look at other examples and make some calculations starting from the definition. In each case here we have assumed this condition that the integral exists, let's say in the first case, for any t that is less than 0, that the integral of 1 over 2x minus 5 exists. Now you see that 1 over 2x minus 5 has discontinuities. In particular, it is discontinuous. In fact, there is only one in this case, but it's discontinuous at 5/2. It would not be in the interval from t to 0 if t is less than 0. So the function is a continuous function on our interval, and therefore the integral from t to 0 of 1 over 2x minus 5 exists for each t less than 0. And so we can consider the limit as t goes to negative infinity. To calculate the integral inside the limit, you see that we can use substitution with u equal to x minus 5, in which case du is 2 dx, so we can replace dx by 1/2 du, and we obtain the limit of 1/2 integral of du over u, and we have to change the bounds. When x is t, then u is 2t minus 5, and when x is 0, then u is negative 5. So now we are integrating from 2t minus 5 to negative 5. An antiderivative of 1 over u is natural log of absolute value of u, and using the fundamental theorem of calculus, because the function is continuous on the interval, the value of the integral is the difference of the values of an antiderivative. Difference of the values at the bounds of integration. So plugging in the values, we get the limit as t goes to negative infinity of 1/2 of the value at negative 5, which is ln of 5, minus the value at 2t minus 5, which is just natural log of the absolute value of 2t minus 5. Now when t goes to negative infinity, absolute value of 2t minus 5 goes to positive infinity, and therefore negative log of this quantity goes to negative infinity. So we end up with negative infinity for the limit, and so since we have an infinite limit, the integral is divergent. Moving on to the next integral, we start out as usual by just writing the definition. It is a limit as t goes to infinity of the integral from 0 to t of x over x squared plus 2 squared. And you see that what we have at the top, x dx, is a constant multiple of the derivative of x squared plus 2. So it is natural to use the substitution u is x squared plus 2. In this case, du is 2x dx. So what we have at the top is 1/2 du. So we replace x dx by 1/2 du, and so we get the limit of the integral of 1/2 integral of du over u squared. And again, we need to change the bounds because in the original integral before substitution, the bounds were indicating the range of values that x takes, and now that we're integrating in terms of u, we have to give the corresponding range of values that u takes. So when x is 0, u is 2, right? Just plugging x equals 0 in the defining expression for u, and when x is t, then u is t squared plus 2. Now, because the function 1 over u squared is continuous on the interval from 2 to 2 plus t squared, we can use the fundamental theorem of calculus to calculate this integral. We just take an antiderivative of 1 over u squared. That's an antiderivative of u to the negative 2. In other words, u to the negative 1 over negative 1. That is negative 1 over u. And so we evaluate this antiderivative between t squared plus 2 and 2. And we obtain 1/2 of the value at t squared plus 2, which is negative 1 over t squared plus 2, minus the value at 2. So we subtract negative 1/2. In other words, we add 1/2. When t goes to infinity, 1 over t squared plus 2 goes to 0, and therefore our limit is 1/4, and this is the value of this integral, which is of course convergent because it has a finite value. In the third case, we integrate e to the negative 2t from negative infinity to negative 1. Again, we start out with a definition in terms of limits. This integral is just a limit as x goes to negative infinity of the integral from x to negative 1 of e to the negative 2t dt. We use x when we were using t in the previous cases simply because now t is a variable of integration, so we need another variable for the limit. So to calculate this integral from x to negative 1 of e to the negative 2t, we just use a simple substitution. E is negative 2t, so du is negative 2 dt. That means we replace dt by negative 1/2 du, and then we have e to the u. So we obtain the limit of negative 1/2 integral of e to the u du, and as usual we change the bounds of integration accordingly. When t is equal to x, u is equal to negative 2x, and when t is equal to negative 1, u is equal to negative 2 times negative 1, positive 2. The antiderivative of e to the u is e to the u, so we obtain the limit at negative infinity of 1/2 of e to the u evaluated between negative 2x and 2, and that is the limit at negative infinity of 1/2 of e to the negative 2x minus e to the 2. Now, when x goes to negative infinity, negative 2x goes to positive infinity, and therefore e to the negative 2x goes to positive infinity as well. That means we have an infinite limit, and the integral is divergent. For the fourth integral, we have an integral defined. We're looking at an improper integral on the entire real line, integral from negative infinity to positive infinity. So by definition, it is the integral from negative infinity to 0 plus the integral from 0 to infinity of that function. Could have picked another value than 0, but 0 will be practical. If one of these two integrals is divergent, then my integral from negative infinity to infinity will be divergent as well. If they're both convergent, then the integral from negative infinity to infinity will be the sum of the values. Let's start with the second integral from 0 to infinity. By definition, it's a limit of the integral from 0 to t as t goes to infinity. And the integral from 0 to t is well defined. The function is continuous on that interval, so we can use the fundamental theorem of calculus and just evaluate an antiderivative. But an antiderivative of 1 over 1 plus x squared is well known, it's just arctangent x. So we have the limit as t goes to infinity of arctangent x evaluated between t and 0. So we get arctangent t minus arctangent 0. Arctangent 0 is 0, so what remains is a limit as t goes to infinity of arctangent t. And you should remember, if you draw yourself the graph of arctangent t, the limit at infinity of arctangent is pi over 2. And therefore, this is the value of our integral from 0 to infinity. We can do a similar calculation for the first integral from negative infinity to 0. Namely, we have the limit as t goes to negative infinity of the integral from t to 0. And again, an antiderivative of the function is just arctangent x that we evaluate from t to 0, so we get arctangent of 0, which is 0, minus arctangent of t. In other words, what we have is a limit as t goes to negative infinity of negative arctangent t. Again, if you remember what the graph of arctangent t looks like, you'll see that the limit at negative infinity of arctangent t is negative pi over 2. Since we're looking at the opposite of arctangent, we obtain positive pi over 2. Therefore, both integrals are convergent, and the integral from negative infinity to infinity is just the sum of the values, pi over 2 plus pi over 2, so we get pi for this integral. Now we have a fifth example, which is the integral from 0 to infinity of cosine squared theta. So, by definition, it is a limit as t goes to infinity of the integral from 0 to t of cosine square, and we have seen several times how to integrate cosine square of a function, cosine square theta. We do that using the double angle formula, and therefore replacing cosine square of theta by cosine of 2 theta plus 1 over 2. Can pull out the 1/2 and then take an antiderivative of cosine 2 theta, which is 1/2 sine 2 theta, and an antiderivative of 1, which is just theta, and we evaluate that from 0 to t. The value at t is going to be 1/4 sine 2t plus t over 2. The value at 0 is going to be 0 because sine of 0 is 0. So we get the limit as t goes to infinity of 1/4 of sine 2t plus t over 2. It is not clear what happens to sine of 2t as t goes to infinity, but in any case, sine of 2t stays between -1 and 1. When we multiply by 1/4, we have something that may oscillate between -1/4 and 1/4. But the t over 2 goes to infinity anyway. So for the limit, we get, again, an infinite limit, and therefore a divergent integral. Now in the next video, we are going to discuss type 2 improper integral.